Welcome to the Introduction to Optimizing FPGAs with the Intel oneAPI Toolkit online training. My name is oneAPI. This is the concluding part of a two-part introductory training on using oneAPI with Intel FPGAs. This training is available for desktop viewing as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the email address provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. At the end of this online training, you will become familiar with optimization reports and how to analyze the information being conveyed about your design in these reports. Also, you will become familiar with and gain an understanding of common optimization methods for FPGAs when using oneAPI. This training will first introduce the concept code to hardware, then go over loop optimization, memory optimization, reports, and some other optimization techniques that are available to use with oneAPI that can enhance design performance on FPGA. We will now begin with code to hardware. This is to give us an overview of how our DPC++ code is converted to a design on the FPGA. When you execute your kernels, the compiler feeds you a pipeline that will be used to build blocks into. This is very similar to how pipelines are built into CPUs. The pipeline built for your design is customized to your design, unlike in CPU where all of the hardware is utilized for an operation. The FPGA does not use extraneous hardware. Thus, clocking and power will be provided to only the blocks used for the design. On-chip RAM is also provided, thus generating a very custom hardware design rather than a general purpose one. Overall, the FPGAs implement custom compute pipelines synthesized from your compiled code. So, how is a pipeline built? Depending on the kernel code, hardware is built into a custom pipeline. Hardware is added for computation, memory loads and stores, control, and scheduling. A pipeline typically has many stages, as many as 200. This picture shows a very simplified pipeline built for the kernel code, which is a vector addition. For this design, an adder for carrying out the computation, a load unit, and store unit is required, and this is built into the pipeline as shown in the figure. Note that in reality, the load and store units are one. In addition to this, a loop control to check how many times the loop has executed and when to quit the execution is built into the pipeline. In connecting the pipelines together, when variable latency paths exist in the operations, they will require handshaking signals, which typically slows down operation. Operations with a fixed latency are clustered together. They are usually easy to operate on. Fixed latency operations improve area since no handshaking signal is required, as well as performance, as there are no potential stalling due to variable latencies. Some designs have operations that can occur simultaneously. The compiler can automatically identify these independent operations. Simultaneous hardware is built to increase performance. For instance, the example we have here can be executed independently without any input from the user. The simultaneous operations is executed by the compiler, requiring simultaneous hardware being built as well to achieve efficient and faster execution. Building simultaneous hardware like this achieves data parallelism parallelism in a manner similar to how a superscalar processor operates. Bear in mind that the number of independent operations that you can execute depends on the amount of hardware resources available to the FPGA. As mentioned earlier, on-chip RAMs are built into the pipeline for the kernel code as well. Custom on-chip memory structures are built for the variables declared within the kernel scope or for memory accessors with a target of local. If an accessor is present in the command scope, the DDR on the board is used for that memory. Load and store units are built within the pipeline to interact with the on-chip memory or the DDR depending on what your design memory needs are. In this example code snippet showing a kernel scope, an array of 1024 is declared after the dispatch function. It will require memory structure built on the on-chip RAM since it is within the kernel scope. The load and store units interact directly with the built memory structure as shown in the picture. Depending on how you want to use the memory structure, there are various properties that you can tweak, such as banking, increasing the width, and so on. We will learn more about memory optimizations later on. We already established that single work item kernels are ideal and recommended for FPGAs. Single work item kernels almost always contain an outer loop. You might wonder, how does parallelism then occur? The way you get the parallelism is a function of the pipelines. The pipelines built for real-world design are normally hundreds of stages long. In a pipeline with multiple stages, after initial latency, you have data sitting at all the stages of the pipeline. Work executing in multiple stages of the pipeline is called pipeline parallelism. You do not need to do anything to achieve pipeline parallelism. You can, however, ensure that data flow is efficient such that data can sit at every stage. The optimization reports can be used to evaluate how to achieve better data flow. When there are dependencies in the single work item kernel, it is resolved automatically by the compiler. The compiler will build a path within the pipeline that will make data flow more efficient. These custom built-in dependencies make FPGAs powerful for many algorithms. In the example kernel code, there is a carry loop dependency due to the accumulate operation. We must retrieve the previous result of the sum to add to it. The compiler knows that it needs the last value generated at the compute engine. So rather than storing it away for retrieving later, it creates a feedback loop into the pipeline structure, making for an efficient and faster performance. FPGAs are very good with carry loop dependencies. More complicated carry loop dependencies are found in genomics and compression. The compiler just puts in a feedback loop rather than pulling previous data from the DDR. How do I use task and still get data parallelism? In GPUs, parallelism is achieved by having many operations run at once. This is referred to as task parallelism. You can achieve same in a single task work group as well. When you program your kernel scope in single task, you must always have an outer loop that will execute your computation repeatedly, that is, again and again. You can perform loop unrolling, and when you unroll your loop, you are asking the compiler to implement more than one iteration at a time, that is, do more instances at a time. In this example, we are performing a full unroll with the pragma unroll command inserted in the kernel code. This will translate to all 3 iterations performed at once. You can unroll any loop, not just the outer loop, and you can perform a partial unroll as well. Note that to perform a fully unroll, you need a constant bound for a terminator. We will look at a partial unroll next. As a side note, unrolled loops still get pipelined. The compiler will still pipeline an unrolled loop. What this implies is that the 2 techniques of pipeline parallelism and loop unrolling is combined. However, a fully unrolled loop will not be pipelined. Only partial unrolled loops can be pipelined. In this example, we have a partial unroll in the kernel scope. It has been set to unroll 3 times, that is, execute instances of this operation in 3s. Since the terminator for this loop is 9, this operation operation will end after the third execution. The figure shows a breakdown of this setup. Note that unrolling loops can take lots of hardware resources to execute. You can achieve task parallelism by having many independent kernel scopes. FPGAs can run more than one kernel at a time. This is similar to multi-threading in CPUs. Pipes can be incorporated into the kernel scope for passing data between kernels. A good example of this can be found in the gzip compression example that is included with your download of the oneAPI based toolkit. The example has 3 independent kernels with kernel-to-kernel pipe structure. Bear in mind that the limit to how many independent kernels that can run is the amount of resources available on the FPGA to build the kernels. We have repeatedly mentioned that single task kernels are ideal and recommended for FPGAs. A good question then is, can we build parallel kernels? That is, kernels launched with parallel 4 or parallel 4 workgroup? The answer is yes. FPGAs can build parallel kernels and provide correct results. However, loop optimization techniques may not apply to them. The kind of algorithms that FPGAs do well are best expressed in single task. For instance, carry loop dependency are not easily expressed in parallel 4. If your design is easily expressed in parallel 4 workgroup, then the GPU will be your preferred architecture. There are 2 major optimization types or functions for FPGAs that can be used to optimize code for FPGA kernels. They are loop optimization and memory optimization. We will first take a look at loop optimization techniques. As a refresher, single work items are usually dispatched or launched with the group handler member function single_task or with other functions without a reference to the work item ID, implying a group size of 1. Single work item kernels contain an outer loop. They do not contain a reference to the work item ID. Remember also, parallel kernels are launched with the command group handler member function parallel_4 or parallel_4_work_group. They contain no outer loops. FPGAs can build parallel kernels and provide functionally correct results, but you won't be getting the best performance out of them. The optimization methods we'll be looking at shortly is not applicable to them. The first concept to understand in loop optimization is initiation interval II. The compiler will infer pipeline parallel execution across loop iterations for your kernel design. The figure shows a simplified pipeline built for the vector addition operation in the example kernel code. There is a representation of the load unit, store unit, and the compute unit. Usually, pipelines that are built consist of hundreds of stages, and these different stages of pipeline will ideally contain different loop iterations. The initiation interval refers to how often we can feed the pipeline a piece of data. The best case for performance is that new piece of data enters the pipeline each clock cycle. In essence, we want to keep the pipeline computing and fed with data each clock cycle, since this is a synchronous hardware. If data flow is at every clock cycle, we can guarantee that we are using the hardware efficiently. Therefore, our target II is 1. When II is greater than 1, optimization techniques should be applied to make the II 1. Serial execution of operation is the worst case. One iteration needs to complete fully before a new piece of data enters the pipeline. In the diagram on the left, serial execution of the loop is conducted, whereafter an iteration performs all 3 operations. It goes back and do it again for subsequent iterations. The diagram on the right shows pipeline execution in comparison. Here we keep the loop structure, but we launch successive iteration as soon as the dependency is resolved. There is a dependency between operation 2 and operation 3, but it can be resolved in one cycle. So in the FPGA, we can simply wire the result of operation 3 to operation 2, and we will be able to launch successive iterations every clock cycle into the data flow circuit, and therefore not stall the pipeline. When loop pipelining is performed, the compiler will report the initiation interval II, which is the launch frequency in cycles of successive new loop iterations. An II of 1 is optimally pipelined, meaning there are no dependencies, or dependencies can be resolved in one cycle. If there are dependencies that takes more than a clock cycle to resolve, the compiler can still pipeline the loop with an II greater than 1. Sometimes you must wait more than one clock cycle to feed data into the different stages of the pipeline. This can be because there are dependencies that are failing to resolve fast enough. Like in this example, the II equals to 6, implying 6 cycles later, the next iteration enters the body of the loop. This is not an efficient use of the hardware because compared to an II of 1, this operation is 6 times slower. Note that we neglect initial latency because it is usually much smaller than loop iterations. The key to better loop performance is to minimize II. Keep it as close to 1 as possible. Let's look at what can cause dependencies not resolving fast enough and eventually leading to high II. When you take a look at the optimization reports generated for your code, you will find the II report in the II column under loop analysis. It will also refer you to the piece of code where the II is problematic, thus giving you pointers to what part of your code needs inspection. In the example provided, we are having an II of 339. This is too high compared to 1. We see in the details section that memory dependency is the reason for this high II. Memory dependency implies that the kernel cannot retrieve data fast enough from memory. This memory dependency can be due to the kernel pulling data from the DDR in a random access pattern. As we can see in this example, the kernel is pulling data from the accessor that has been declared in the command scope. There is no pattern in the pulling of the data from the accessor. When you pull data from the accessor in the command scope, you are pulling data from the DDR. Pulling data from the DDR in a random access pattern can cause a high II. If you must pull data from the DDR, you want to ensure that you are accessing the DDR in a contiguous pattern so as to achieve a good II. Memory dependency can also occur when accessing on-chip memory. This means arbitration is occurring in your design. In such a case, there are further evaluations that you can try out to combat this. Next, we will look at ways to improve II if you must access the DDR in a random access pattern. So what can you do if you're pulling data from an accessor in a random way and you have a bad II like in the previous example? You can transfer the data to on-chip RAM and access the data from the on-chip RAM. That means you transfer global memory content to local memory before operating on the data. How do we do this transfer? We create an array inside of the kernel code and we hand off the data from the accessor into that array in a contiguous pattern. In this example, we see the initial code is pulling data from the DDR in a pattern that is not exactly defined. The improved version creates an array B inside of the kernel and transfers the global memory content A into B first before performing the random pattern operation on the data, after which the results are transferred back to the global memory in a contiguous pattern, bringing about an optimized performance and eliminating the random accessing of the DDR. Sometimes you can have memory dependency because from one loop iteration to the next iteration, the compiler believes that an access had to be finished first before continuing. This example here shows something that can be interpreted that way by the compiler. Looking at A, the compiler can predict a dependency. You can ask the compiler to ignore dependencies by using the construction Intel FPGA : ivdep, just as shown in the example code. You can ask the compiler to ignore dependency for a specific array only by declaring the array in the ivdep construct. The second example shows dependency will be ignored for array A but will be enforced for array B. Be careful when using this construct, as you might break the code functionality if dependencies actually does exist in your code. Another reason why II can be very high is due to data dependency. This means that the kernel cannot complete a calculation fast enough. The report we have here shows an II of 38, which is also a high II compared to II equals 1 for best performance. The details section has it that data dependency is responsible for this. When we inspect the code, we can see that the compiler is having to perform difficult double precision floating point operation, waiting on 4 divides operation to finish first before it is able to perform the next divide. This will definitely take a while, and generally divides are slow. Reading the details field below in the report, it shows the divide is taking 36 clock cycles, thus accounting for the high II. Data dependency can also occur when you have more than one operation or implicit conversion. The report will tell you what calculations or operations are contributing to the overall latency. What can you do if you have a high II due to data dependency, that is, computation that is taking too long to complete? You can try to simplify the calculation. This might be a bit challenging. However, since you are coding at a high level for FPGA, you have more flexibility in coming up with a simpler computation. You can try to pre-calculate some of the operations on the host, especially operations that require divide. The host is better at division operations than the FPGA. You can also try to use a simpler data type. In the previous example, we used double precision data types, which is an expensive data type in terms of computation. You can try using floating point operations, which we will look at later on. A more advanced approach will be to increase time, that is, the pipeline stages between the start of calculation and when the result will be used. You can read more about this in the relaxed loop carried dependencies section in the optimization guide. Loop unrolling is also a technique that can be used to optimize your loops. Bear in mind that using loop unrolling involves a trade-off between how much hardware resources is utilized and how fast your computation will be. This is because you are directing the compiler to perform more computation at once instead of launching the loop more times. Sometimes it may not be able to perform loop unrolling, and usually the report will show this information and also provide the reasons why it was unable to do so. The compiler's prerogative is to optimize II first. However, the maximum frequency Fmax achieved is also important. The Fmax refers to the clock rate the FPGA is clocked at, and it depends on what hardware your kernel compiles into. The more complicated the hardware, the slower the frequency. The whole kernel will have one clock, and where there is a slow operation, it can slow down your entire kernel by lowering the clock frequency. Typically, the compiler will sacrifice a higher Fmax for a lower II. What if you are more interested in getting a better Fmax? We will look at ways you can let the compiler know this. You can find the target frequency for each loop in your code in the optimization report under the loop analysis section. This Fmax is a theoretical value. See how each block in the report on your screen has its own Fmax shown. Since the entire kernel will have only one clock, it means all of the blocks inside of the kernel will have one clock. The block here that has a frequency of 106.5 will eventually be the kernel clock frequency, thus slowing down the entire kernel despite the others having a higher clock frequency. It is good to pay attention to the Fmax because you may have a block slowing things down that you do not really care about, and you can trade off II for a higher Fmax in such a situation. How do you tell the compiler to prioritize Fmax over II for a particular loop you do not have much care for? You can do so by introducing the attribute as shown in the slide. The n represents the target value you are comfortable with, and usually it should be greater than 1 or whatever the report returned it as. Giving n a lower value does not ensure priority. When we use this attribute, the compiler gets a new direction on ignoring making II as low as possible. In the previous example, II was 2, so if we are interested in obtaining a higher frequency, we will give n a value higher than 2. This will in turn push up the Fmax. On rare cases, using this attribute may not bring about a higher Fmax, but generally, this is a rule of thumb. Area might be something you are interested in and you care about. Normally, the compiler will sacrifice area for a low II, implying that you have taken much area to accomplish that II. If you would rather have area available, you can use the attribute as shown to give up II, setting n to a value higher than the initial report showed. Also, you can have concurrent operations going on to keep the pipeline fed with data constantly. If you want to suppress that behavior and are not interested in the performance of that loop, you can use the attribute for maximum concurrency, which is Intel : max _ concurrency to achieve a smaller area. We have looked at the various techniques to optimize for loops. Next, we will learn the various ways we can optimize for memory. There are different types of memory resources available for you to work with when writing DPC++ for FPGA. Whenever you pull data from an accessor in your kernel scope, you are accessing the DDR on the FPGA board. The DDR is made available since it has a higher memory capacity than the on-chip memory. This table shows the board memory resources available on the Area 10 board. There is 8 GB of memory in the DDR on the Area 10 board. The disadvantage of using the DDR is that the latency for random access can be large. In worst cases, random access is 240 clock cycles. Hence, when designing, it is good practice to keep this in mind. The on-chip RAM has the advantage of lower latency for random access with a worst case of only 2 clock cycles, providing much better performance in comparison with the DDR. However, it has the disadvantage of having a small storage capability, with the Area 10 board having 66 MB as shown in the table. Another type of memory resource is the register. The registers are very fast, having a 2-to-1 clock cycle for random access. Whenever scalars are declared, they are usually implemented as registers. When global memory access is slow, what do you do? The example here is one we have looked at previously and will appear in the optimization report as a memory dependency problem. An optimization technique for this is to either make the access to the DDR or the global memory contiguous, or utilize local memory by declaring an array inside of the kernel scope, thus transferring the data into the array in a contiguous manner, and after the random computation is completed, transferring the result back to the DDR in a contiguous manner. What if local memory still has bottlenecks? When there are bottlenecks in local memory, it will show up in different ways. One way is how the II is reported. If you find there is a less than or equal to in front of your II value, it implies that there is arbitration happening inside of the local memory. In the report, there is a section where you can look at the local memory structure, and where there is arbitration, it will show up as seen in this figure. The ARB represents arbitration and will show up in red. When arbitration is built into your local memory structure, it is not good because it implies that inside your kernel there are more load and store points trying to access the local memory than there are ports available. The different load and store points have to wait their turn to implement, causing a stall. Your goal is to get rid of all arbitration in the local memory. Remember that local memory is the arrays that you have declared in your kernel scope. Let's now look at various ways to fix this. The compiler is going to try different methods to optimize your design. You just need to know the technique that is available for the compiler to use, such that you can design for these techniques to be taken advantage of. Natively, the local memory has 2 ports. Kernels will very likely require more than 2 native ports, which is native to the FPGA on-chip memory. Thus, how do we convert our 2 ports into more ports? The first thing that can be done to optimize for arbitration is to double pump the native ports. What do we mean by this? We have a kernel clock cycle going at a rate X, and then we have another clock that is available to use with memory at twice the frequency. We proceed to clock the memory at twice the frequency, putting a mux in front of the native 2 ports and alternating every other clock cycle the data that is to be fed into the ports. This essentially makes the 2 ports into 4 ports just by double clocking the memory at twice the frequency and muxing at the ports. Before implementing the double pumping method, we inspect the code, checking for how many load and store points are in the kernel. If there are more than 2 and up to 4 points, the double pumping technique is applied. The only drawback of this technique is that if you have a kernel that was really fast, when you double pump the memory, it will become twice of that clock rate. Another optimization that can be done is to replicate the memory. Like in this example, we have an array that holds 10 24 integers. The compiler can build a duplicate structure such that you get 2 structures each holding 10 24 integers respectively. The obvious disadvantage is that this method takes up more FPGA resources to build the duplicate structures. The not so obvious disadvantage is that for every replication, whenever a storage occurs in that instance, a storage usage must also be made in all the duplicate copies of the structure in order to maintain coherence of all the content. With this technique, a double pumped memory, which is now 4 ports, becomes unlimited ports. There is no sense using memory replication as an optimization if the operation is having more than 3 stores happening at a time, since there has to be replication in all of the copies made. The ideal situation for this technique to be implemented is for a kernel having a lot of load operations instead. In the example shown, the loop is fully unrolled, signifying all 9 iterations will launch at once. Notice how there are 9 loading operations for every store, making this a very good candidate for replication. Remember that the compiler takes care of all of this for you. Yet another optimization technique is coalescing, which widens the ports. In this example, both loops are fully unrolled. There are 4 store operations happening at one instance of time and 4 load operations happening at one instance of time in the kernel. The compiler can coalesce the integers together, which means making the ports wider. So instead of having 1 integer in width, it becomes 4 in width, such that 4 integers at a time is pulled in one load operation at a time, and 4 integers at a time is stored in one storage operation at a time. The compiler will check if the access is contiguous before implementing the coalescing technique. The final technique we will look at for optimizing the local memory is called banking. Banking means that one array is built into multiple banks rather than one big memory structure. These multiple banks will act independently and will become fractional pieces of the array. To determine if this method can be utilized, the compiler looks at the lower index of the array if it is a power of 2. It also looks at the manner in which the array is being accessed. If the access is such that it is possible to access the array independently. As a general rule, try to code in a pattern that can be optimized by the compiler. At first, let the compiler try on its own to achieve memory optimization because it does a good job of finding the best optimization techniques for your kernel. If you realize the compiler is unable to do so or you want something special, there are attributes that can be utilized. The list shown here isn't exhaustive. You can check the optimization guide to find more and learn their behavior. A memory structure that is available and you can take advantage of is the pipe. Instead of talking through the DDR from kernel to kernel, you can send data from one kernel to another and the compiler will build pipes for you. Pipes can be a wired structure which can have depth. You can put in a FIFO as well and the kernel will just pass data into another kernel. To utilize pipes, you will have to design your kernel from an architectural standpoint. Using pipe is extremely advantageous since data doesn't have to wait before being passed from one kernel to another kernel. Inside of your code, you will have to declare a custom class at the top scope. Once this is declared, you can just write into the pipe by giving it a value and read from it by returning the value. For more examples, check out the oneAPI tutorials available on the Intel Dev Cloud. With this, we have come to the end of memory optimization techniques. Next, we will look at the optimization report and some of the components in it and how to analyze them. The static report is usually in a HTML form showing optimization, area and architectural information located in the report directory of your project after executing the optimization report generation command. It is automatically generated with the object file. It provides dynamic reference information to original source code. Note that reports change looks with every release, but the sections will always remain the same. The first section of the optimization report is the throughput analysis section. This is where the loop analysis is reported. It has columns for II, Fmax, and some other components which we didn't discuss. You can read more about them in the optimization guide. The report contains very good details about blockers and actionable feedback on pipeline status of loops. Try to make it a habit to always read the details section. Another section of the optimization report is area analysis. This section tells you what percentage of the FPGA hardware is being utilized. It gives information on hardware utilization block by block, providing architectural details of hardware and suggestions on how to resolve inefficiencies. It breaks it down into lookup tables, flip-flops, DSP blocks, and RAMs. It is good to keep an eye on each resource that is being used such that it doesn't go over 100% of the area being used. It is good practice to read through the details reported. There is also the graph viewer. This shows how the pipeline feeds into each other, the load and store points of each of the pipelines, and how they are connected. The global memory as well as the local memory are shown in here in a pictorial form. You will be able to see what kind of load and store points were implemented for your kernel when we hover over it. In this report, we can see that burst coalesce was implemented for the local memory. If pipes were used in your design, it will also show up in the graph viewer. The graph viewer gives you an idea of the overall structure that has been implemented by the compiler for your design. The schedule viewer is another section in the optimization report. It shows how data travels in the pipeline at every clock cycle. The schedule in clock cycles for different blocks in your code. You can start to get a very fine-grained picture of that pipeline's performance and where the bottlenecks are in the calculation. The next section we will look at is the kernel memory viewer. All the arrays that has been declared in the kernel scope will be built up with on-chip memory. The viewer gives you a view of all the memory structure that has been built, illustrating memory replication, banking, implemented arbitration, and read-write capabilities of each memory port. The viewer helps you identify data movement bottlenecks in your kernel design. We have successfully looked at two types of optimization techniques: loop optimization and memory optimizations. Next, we will look at some other techniques we can use to optimize our kernels. When programming the kernel for an FPGA, try to avoid using expensive functions. Expensive functions refers to things that are big in hardware, and since they are big, they slow down the kernel. For instance, division and modulo are slow on the FPGA. It is best to pre-compute these operations on the CPU. Other examples of expensive functions are floating point operations that are not addition, multiplication, absolution, and comparison. Also, atomic functions. Typically, you can't code up atomic functions in single task. But if you are using parallel for on FPGAs for atomic functions, bear in mind that these are large functions and are slow. Try to use inexpensive functions as much as possible. They have minimal effect on kernel performance and consume minimal hardware. They are small and thus fast, and you can get the best out of your FPGA by using them. Examples are binary logical operations such as AND, NOR, NAND, XOR, or XNOR. FPGAs were originally built for logic operations, hence they perform very fast on logic operations without taking much hardware. Shifting is small and fast, and integer multiplication and division by a constant that is to the power of 2 will be implemented as a shift. Also, bit swapping is very small and fast as well. Try to use least expensive data type. Double precision floating point is going to be very slow and very big on the FPGA. It can use more than 4 times compared to what a single precision would use. DSP blocks are natively designed for single precision. That is why double float operations is so much bigger, because it must use soft logic, lookup tables, and flip-flops rather than just using the DSPs alone. Latency may be much larger for float and double operations compared to fixed point types. Thus, if possible, use floats instead of double. That is so much better for the FPGA. Arbitrary precision libraries are also available that you can take advantage of. You can use fixed point instead of floating point, as this will be smaller and faster compared to the floating point. There is also half precision available sometimes, but with the DSP blocks, it is best for single precision than half precision. In general, use least expensive data type resources. When using floating point data types, there are a couple of optimization you can turn on. Bear in mind that these techniques are not compliant to the IEEE standard for floating point arithmetic, that is IEEE 754/2008. Two techniques that can be used for floating point optimizations are tree balancing and reducing rounding operations. We will look at each of these techniques shortly. Floating point operations are not associative. For instance, addition or multiplication are not associative due to rounding after each step. Usually, the compiler is not going to reorder the floating point operations, which can affect latency and area. This operation may create an imbalance in a pipeline, cost latency, and possibly area. You can tell the compiler to relax reordering rules manually. To do so, set the XSFP relaxed flag to true as shown when calling DPCPP. Bear in mind that these optimizations will cause small differences in floating point results. The second technique for floating point optimizations are rounding operations. For a series of floating point operations, IEEE 754 require multiple rounding operation. This is done by building custom hardware for rounding up, which can require significant amount of hardware resources. You can fuse the floating point operations together by performing only one round at the end of the floating point operation tree and just carry the last bit at the very end. Any combination of floating point operators can be fused. Other processor architectures support certain fused instructions such as fused multiply and accumulate (FMAC). This optimization technique may not produce a very accurate result, but if you're not concerned about exactness and accuracy, then you can tell the compiler to perform rounding operations by turning on the -XSFPC switch. As a rule, when using floating point operation, it's best to set all the flags to true. On your screen are various resources that you can explore. The website hub provides lots of information on the tools and components for using FPGAs with oneAPI. The Intel oneAPI FPGA handbook is rich in information that can get you started on creating your own design. We have tutorials that can give you hands-on practice, also available in GitHub. We have come to the end of the training, Introduction to Optimizing FPGAs with the Intel oneAPI Toolkit. To summarize, a brief recap on what we have learned. Loop optimization techniques and memory optimization techniques can be exploited to achieve better performance of FPGA kernels. The compiler takes care of implementing these techniques provided the DPC++ model is designed in the proper form. Static reports provides ample information on what the bottlenecks are in the design, what the compiler has attempted to resolve, and recommendations on how to fix it. Intel provides multiple avenues in which to learn about Intel FPGA products. There is the Intel FPGA YouTube channel, which contains 5-minute quick videos along with longer, more in-depth training videos. There is the Intel FPGA training website, where you can access e-learning courses made up of narrated slides presented in an interactive player, some courses with labs and demos. Lastly, you can also enroll in a live instructor-led course. All instructor-led courses have hands-on labs, exercises to practice the concepts you learn. If you need more assistance, Intel FPGA provides many self-help resources for you to access. For example, there are web pages called landing pages dedicated to specific FPGA technology, like high-speed interfaces. You can also view and post questions to the community forum, which is monitored by skilled Intel FPGA applications engineers. The Intel FPGA training team is always looking to improve our material and welcome any feedback you may have. Please email fpgatraining@intel.com with any of your thoughts or comments. This concludes the training. Again, my name is Ogene Uriri. Thank you and have a good day.